Welcome to this, this video on how to sketch the curve of a function. This is a rather long PowerPoint. I'm not going to go through every slide that we have here. I did want to do just two types of problems for you though, as those are going to be problems that you see in Newton later on. So we're going to look at how to actually sketch the curve of a function, and we're going to do this without the use of a calculator. So we're looking at a polynomial function and a rational function. We're not going to work with those functions that have cusp. We're only going to do the polynomial and the rational. So you might want to print this screen and this screen, as they give you kind of a 6-step approach to how to do this. Okay, so we're going to be looking at the domain of our function. We're going to look at the x and y intercepts of a function. We're going to be looking at the limit as x approaches infinity and negative infinity, and that's something we did in this class in one of those previous sections. We're not going to be dealing with a whole lot, excuse me, I have a random pen mark here. We're not going to be dealing with a whole lot of oblique asymptotes, but we will see those, and so I'll explain what those are as we get closer here. We want to talk about vertical asymptotes, and again, as we go through these, I'll remind you of those things. This is where we focus on the new stuff, okay? So steps 1 through 4 should be things that you've already seen in previous math classes. Steps 5 and 6 are things that we went through in this class just in the last couple of weeks or days, depending on what pace you're working at this class. So in section 5, or in step 5, we're looking at finding critical points, talking about intervals of f being positive, increasing, or f being f decreasing, where the derivative is negative. So in this step, in step 5, remember, we're going to set the derivative equal to 0, and that's going to give us those critical points. Okay, so you're going to have to use a chart for, if you recall, we had negative infinity to say negative 1, and then we had negative 1 to infinity, and we talked about plugging values into the derivative to find out if it was greater than 0 or less than 0. So that's going to be something we do in step 5, and again, that's the approach in step 6 where we talk about concavity. So without further delay, let's jump in here and do one of these problems. So what I want to point out to you first is if I square x minus 1, okay, I get x squared minus 2x, excuse me, plus 1. And I'm going to multiply this by x plus 2. So here's what happens. Our function could be rewritten as x to the third plus 2x squared minus 2x minus 2x squared minus 4x plus x plus 2. So let me focus in right here. This was negative 2x times 2 and negative 2x times x. So that's where we get our negative 2x squared. Now, we want to make sure that we cancel things that should cancel, combine like terms. So in effect, an alternate way of writing our function would be to write it like so, okay? You're going to see this pop up later on in this PowerPoint, so I just wanted to have that handy so that you would know where that comes from. Now, this is a polynomial function. In other words, there are no division signs, there are no square roots. So when I think about the domain of a polynomial function, it's the set of all real numbers. In other words, the domain is negative infinity to infinity. Step 2 was to go in and find the x and y intercepts. So when x is 0, we get a y value of 2. So one thing to note, what's happening here is to find the x intercepts, right? We solve the equation. So in essence, we set y equal to 0 to find x intercepts. And we switch that around, we set x equal to 0 to find y intercepts. Okay, and that was, again, that's done right here. We see when x is 0, we get 2. So our y-intercept turns out to be 0, 2. And then the x-intercepts are going to come from this version of our equation. The version that I circled here is much easier to work with when we're trying to find those x-intercepts. all I'm going to do to find those x-intercepts is set each of those things equal to 0. X minus 1 equals 0. X plus 2 equals 0. So that gives me an x-intercept of 1 and negative 2. And you can see how that plays out here, 1 and negative 2. Again, the y value for those is 0. From a previous class, you learned about end behavior. And so what happens is as we put very, very large numbers into this function for x, we find out that our y values become very, very large. Okay, so the end behavior just tells me what's going on out at each end of the graph. So right here, as x approaches infinity, that's what that arrow means, our function is going to approach infinity. In other words, the limit as x approaches infinity is infinity. Here's what that would look like on a graph, right? Out here at infinity, our y values are going up, okay? Now, when we plug in negative infinity, that's what this means, right? Finding the limit as x approaches negative infinity, we're plugging a very large negative number in here. And when I square a negative number, I get a positive number. Now, if I plug a very large negative number in here for x and I add 2 to it, I still get that very, very large negative number. And a negative infinity times a positive infinity would give me a negative infinity. So out here on this left side of the graph, way out here at negative infinity, our y value is getting very, very small. Okay? All right, so all of that was old stuff that we've looked at. We can get even more information if we look at the end behavior. The leading term of this thing is positive, right? The leading term is 1, and because the exponent is odd, we can say that this thing is going to look more like this here. And what we want to focus on is what's going on in the middle. And that's where steps 5 and 6 come from. So if you recall, we rewrote that function as x to the third minus 3x plus 2. Our derivative then would be 3x squared minus 3, and that derivative shows up here. Now, there may be a typo on one of your PowerPoints if you're looking in Canvas here, and I believe it's right here. I think in Canvas they have this is a 2, and this was an error by by the publisher. So just in case you see a 2 right there on your PowerPoint, it should be a 1. This thing will factor into x minus 1, x plus 1, and we're going to set each of those equal to 0, and that gives me critical points of 1 and negative 1, okay, and they show up here. Now remember from our previous sections, what we do is we set up these intervals and we plug values from each interval into the derivative. Okay, so if I take a value like negative 2 and I plug that into the derivative, remember the derivative was 3x squared minus 3. Well, if I square negative 2, I get 4. 4 times 3 is 12, and 12 minus 3 is a positive value, right? So what that tells me is on this interval, the function is increasing, okay? And we have that showing up right here in this chart. Kind of small, but it's there for you. A number between negative 1 and 1 would be 0, and if I plug that 0 into the derivative, I get a negative 3. In other words, my function is decreasing. So there's something important we can say here about x equal negative 1. We can say that it is a relative max. Okay, so we're getting some valuable information about our graph as we go through here. A number from this last interval that I can plug in, maybe like 2. Okay, so if I plug 2 in, I'm going to get a value very similar to plugging in negative 2. In fact, I'm going to get the same thing. And I can say that f is increasing on that interval. That's important because when x is equal to 1, I can say that I have a relative minimum. Okay, my function was decreasing, now it's increasing. So last step is to look at the second derivative. The second derivative of this thing is 6x, and if we set that equal to 0, we get x equals 0. So I'm going to go in and plug in, I'm going to look at these two intervals from negative infinity to 0 and 0 to infinity. If I plug a number from this value into the second derivative, I find out that that's negative. So that tells me on this interval, my function is concave down, okay, all the way up to 0. And then when I plug in a positive value, I can tell that the second derivative is greater than 0, and my function is concave up. All right, so let's take a look at what we're able to generate then. So I knew that I had x-intercepts of 1 and negative 2 based on what we have here. And I knew that as we go out to the right and as we go out to the left, out to the right, my function is going to keep going up towards infinity, and over here it's going to go towards negative infinity. I was able to tell from the first derivative that I had a relative max at negative 1, right? So at negative 1, I got that relative max, and I can plug that into the original function to find that y value. I also knew from my chart in step 5 that I was going to have, sorry, we're doing a little autosave. I knew from my chart that I was going to have a relative min right here at positive 1. Okay, so here's my relative or local min and my local max. And then right there at 0, I knew there would be a point of a point of inflection because the concavity changes, right? So this is concave down on this interval, and we're concave up in this interval. So I have a point of inflection right here at x equals 0. Now, you're not actually going to have to go in and physically graph these in Newton. You're going to be choosing from 4 options. So what you want to do maybe is to sketch out what your function might look like based on what the information provided is. Now, one thing that we did not do in our PowerPoint is to find out where this 4 came from. So if you plug in negative 1 to the original function, okay, plugging into the original function gives us those y values. So negative 1 squared is negative 2, and if you square negative 2, you get 4. And we're going to multiply that by positive 1. So that's where we figure out that f of negative 1 is equal to 4. Okay, so just plugging that value into the original function. Okay, you can do the same thing with 0. You can plug 0 into the original function. 0 minus 1 squared is negative 1, and when you square negative 1, you get 1. And 0 plus 2 is 2, and 2 times 1 is 2. Notice at 0, I have a y value of 2. Come back in the next video, and we're going to talk about how to graph another one of these, but it's going to be a rational function. Now, we do have another example for you to kind of go through. So before we jump into that next video, I did want to show you this, okay? And this is going to be more like what you see from Newton. In this, you have to figure out which graph most closely represents the function. And so there are some steps, right, 1 through 6 that we can go to. And some of those steps are going to help us out quicker than others. Here's what I mean. Each of these graphs represents polynomial functions. In other words, there are no vertical asymptotes, no cusp. So I know that A, B, and C could be one of my answers based on step 1, where we talk about the domain, right? So because these are polynomial functions, there are no points of discontinuity, right? No vertical asymptotes. If you look at step 2, where we talk about the x and y intercepts, okay, to find the x-intercept, we're going to set this thing equal to 0. And to find the y-intercept, we plug 0 in. So when I plug 0 into the original function, I get 0 minus 1 squared plus 0 plus 1. This whole term right here, thought I changed colors. Sorry. Let's try that. This whole term is going to turn into a positive 1 times positive 1, but think about this negative out front. So f of 0 equals negative 1. Well, if you look right here, when x is 0, our y value is way down here. This couldn't be our choice. When you plug in 0 for choice B, right, you notice that the y value here is positive 1. That can't be my answer because my answer has to have the point 0, negative 1. So we have choice A. There's another PowerPoint that walks you through one that's a little more in depth, okay? So you can take a look at that one. and then come back and we're going to look at how to sketch the graph of a rational function.